In this video, we'll keep using the concept of the conservation of angular momentum, and we'll be looking at some more collisions. Um, so here, let me go ahead and change this. Here we have a rod that's at a fixed point P. It's free to rotate about P, that's our axis of rotation, um, but it's fixed to it. What's going to happen is we're going to launch this moist clay. So the little ball here, mass M, initial velocity, I'm sorry, it's velocity V naught, and it's aimed at the lowest point of this rod. The rod has mass 5m, length L. And we say it's moist clay. On the AP exam, they'll give you examples of stuff like this where the clay is going to collide but stick to the rod. And so it goes here and hits here. After the collision, here is the rod, and here's initially that plane in which it was. And the rod and the clay are going to move with some angular speed initially after the collision there. Okay, so the question is, we want to know, what is that angular speed after the collision, right after the collision? And we're going to use the concept of angular conservation of angular momentum. So here are the two pictures. Like the left side of the splat and the right side of the splat are our two pictures. If you look at the picture on the left, okay, which one of these has angular momentum? And some people will say there is no angular momentum. Some people will say there is. Um, Clearly, the rod is not moving, it's not rotating, it's not moving. It has no angular momentum, but the moist clay does. And the equation for that is, we learned in the last video or last time, is RMV, just for the clay. Okay, and we're going to calculate that here in just a moment. On the right side, the angular momentum, because this rod clay system is rotating, is just going to be I of the system times omega, and that's what we want to figure out. And I can go and say final, and this is the initial. So let's solve this for real. Um, the initial angular momentum, I think I'll do this over here, is equal to the final angular momentum. Everything on the left here is the initial. That's RMV. Okay, let's deal with R right away. We need to draw a line of action of V naught. And then we're going to draw R from the axis of rotation to the line of action of V. And you can go back to the video in the last, go back to the last video and see about what we're talking about here. We defined R as a distance from the axis of rotation to this line of action. So what is that distance in terms of L? Well, the answer is L. It's the length of the rod. So we'll put L, I'm looking over here, right? So that's L times the mass of the clay times the speed of the clay, that's V naught. Now I need the rotational inertia of the system. Now here we have a rod about one end, that is ml squared over 3. And we're going to need to add to that the rotational inertia of that blob of clay, which we're going to treat as a point mass. If we call m1 the rod, we can call m2 the clay times r squared. Excuse me. So let's put this in values that we actually know. So we know these values here. So again, it's the rotational inertia of the rod goes first. Let's put that. So that's 5m. The length of the rod is just L, so that stays as L squared over 3 plus the mass of the clay, which is just capital M, and the distance r, which is not that r anymore, it's a different r. This is the distance r, it's at the end of the rod. It's still L, but conceptually it's a different r times omega. Cool, and let's just kind of clear up this fraction in here. So this is 5/3 ml squared plus ml squared. We'll get a common denominator of 3. And so that's 5 ml squared over 3 plus 3 ml squared over 3. So this is 8 ml squared over 3 times omega. We can cancel an L from both sides. We can cancel an M from both sides. This is V naught equals 8L omega. I just moved it to the top of the fraction there. And we want to solve for omega. We'll multiply by a 3. We'll divide by an 8L. So that's an interesting result. The initial angular speed, I shouldn't say initial, the angular speed of that rod clay system is 3V naught over 8L. So if the clay has a faster speed, if V naught was increased, that will increase the angular speed of that system after the collision. That makes sense. If the rod were longer and the clay still hit the end of it there, then the angular speed would be less. Let's do another example. We have a rod, mass 3m, length L, that is free to rotate around point P. It's a fixed axis. A ball, mass m, initial velocity v naught, is aiming at the lowest part of that rod. They will collide. The ball does not stick, it bounces back with less velocity, that's v naught over 3, moving backward. And now the rod is rotating about its center of mass there, point P, with some angular speed omega. Well, we want to know what is omega. We'll do the same thing. We'll look at the angular momentum on this side, and we'll look at the angular momentum on this side. Let's start first with over here. Clearly, the rod has no angular momentum. It's all in the ball, the ball there. Whoops. We'll draw a line of action of v naught, and we'll draw distance r. So from the axis of rotation to that line of action, this is that distance r. Okay, doing all these different colors is not too important. But in terms of L, what is r? Well, it's half of the length of the rod. Okay, um, and I should have done this. Sorry. This is r and v. The mass of the ball is m, and velocity is v naught. So if I were to put this all together, this would be m l v naught over 2. Okay. On the right side, the ball has angular momentum and the rod has angular momentum, so we'd actually have to combine them. But I'll do this separately here. So L of the ball, and we can make this initial, by the way. L of the ball over here is RMV, and we'll do the rod here in just a moment. R in terms of L is still the same R. Here's the line of action, and here's R. It's still just half of the length of the rod. The mass is still M, Don't need to do that. But V is now V naught over 3. But not only that, this is momentum. And so the question is, does direction matter here? Because this one is moving to the right, this one's moving to the left over here. And if you recall linear momentum, momentum is a vector. And same thing with angular momentum, direction matters. So there actually needs to be a negative in this. I should just do that white there. Now, if I were to clean this up, this is ML V naught over 6. And again, I forgot the negative. Cool. And let's look at the angular momentum of the rod. It's just going to be I of the rod times omega. The rotational inertia of the rod, I'm going to put the little equation up here. This is ml squared over 12. The rotational inertia about its center of mass. So the mass of the rod is 3m. The length is L, so L squared over 12 times omega. So the angular momentum of the rod is ml squared over 4 times omega. Now, I did it all separately. You could have started, because we still haven't even gotten to finishing the problem. We could have started L1 equals LF, but I'm just illustrating here that each of these has an angular momentum. Sorry, not the rod initially, but the ball here and these two objects here. So the initial angular momentum is just this term. This is M L V naught over 2. And the angular momentum after the collision is this term plus this term. So I'm going to put a negative. Let's not forget about the negative. ML V naught over 6 plus ML capital M L squared over 4 times omega. And we need to solve this for omega. That looks hard, but it actually comes out pretty like to a pretty nice term. Pretty nice expression is what I meant to say. We can cancel m's. There's an m in every term. We can cancel it. We can cancel one L from every term. Very careful here, just the 2. We're left with V naught over 2 equals negative V naught over 6 plus L omega over 4. We can add V naught over 6. And we'll get a common denominator here. This comes out to 4 V naught over 6 is L omega for 4, which I'm just going to reduce this real quick. This is 2 V naught over 3. And if we multiply by a 4 and divide by an L, we should get 8 V naught over 3 L is equal to omega. Kind of similar to the last one, right? You have a term that's V naught over L. Okay, but that's it. Cool, and then let's just finish this up. Okay, this is the last one. We have a ball mass m, a velocity V naught is going towards the top of a rod that's just floating around in space. It's not on a fixed axis of any kind. The rod has a mass 6m and the length of it is L. And again, it's going to collide with it. So that kind of separates our two pictures. Here's one picture and here's the other picture. After the collision, the ball is moving back this way with velocity v naught over 4, so a fourth of its initial velocity there. Now this dotted line shows where the rod used to be, and I should make this lower, something like that, where the rod used to be. And the rod doesn't only start to rotate about its center of mass, but it starts to move tangentially with a speed v. And we want to know what is the rotational speed of the rod and what is the translational speed of the rod v. So two unknowns, we're going to need two equations. We'll start the same way we've been doing these. I'm going to start here. This time I'm just going to go right away with Li equals Lf. Now again, this doink separates the two sides of this equation. So we have one side here and we have the other side here. The initial angular momentum of, here I'm just going to write it down, L is equal to RmV. The initial angular momentum is in this ball, so that's R times M times V. Question is, what is R? And so you can pause the video, think about it for a minute. The center of mass is going to be our axis of rotation, so that would be here. R, and should have drawn this the other way. Here's the line of action of V. R is the distance from the center of mass to the line of action. So R would be this distance here, which is of course half the length of the rod. So this would be, let's go back. This would be L over 2 times the mass of the ball, which is M, times the velocity of the ball, which is V naught. Okay, after the doink, we have angular momentum in the ball here, and this has rotational angular momentum. So let's look at the ball first. Okay, the center of mass is here. Essentially what I'm trying to get at is here is the line of action of V, and center of mass was there. So, oops. Anyway, my point is R is the same value. It's still half the length of the rod. Now, I didn't draw this very well, okay? The rod should be a little bit lower somewhere over here. But anyway, start over. It's just a picture. I just drew it fast. So this is L over 2, the mass of the ball, and this is negative V naught over 4. That is the angular momentum of just the ball. We need to add the angular momentum of the rod. So this was L is equal to RmV. This one is L is equal to A omega. So this is the rotational inertia of a rod about its center. So we need to look here. Okay, so the rotational inertia of a rod is ml squared over 12, about its center is ml squared over 12. The mass of the rod is 6m. The length of the rod is L over 12 times omega. Cool. This looks complicated. It's going to simplify again to a very nice term. So let's do this in parts here. Let's say ml v naught over 2. I'm just kind of making it look nicer. This will be negative ml v naught over 4 times 2 is 8, plus 6 over 12, that's 1/2. We'll say ml squared over 2 omega. Cool. Let's finish up the algebra here and divide everything by an m. Cancel out an m. You can cancel out an L, just one from over here. we are left with V naught over 2 equals negative V naught over 8 plus L omega over 2. We'll add V naught over 8 to both sides. Get a common denominator for this term, for these terms, which will be 8. So that's 4 V naught over 8. We add those together, we get 5 V naught over 8 is equal to L omega over 2. We'll get omega by itself. We'll multiply both sides by 2. And we'll divide by L. Right, so multiply by 2 and divide by L. Looks something like this. And I'm just gonna write this over here. This is 5 V naught. So 2 and 8 will reduce to 4, just like that. So again, omega is V naught, some ratio or some fraction of V naught over L. Cool. So we found omega, and now we need to find V. So you might be thinking there's a relationship we know that V is equal to R omega. But I wrote this down so we can specifically so we can cross this out. Um, this equation works for like rolling motion, where you have like a wheel that's rolling on the ground and there's no slipping. And so this, sorry, this is related to the velocity here. But in this situation, V is not related to omega. This is just spinning in space here. In other words, they're not related. And so we can't use this. Instead, we're going to use something we actually already know. We did this last semester. If an object is moving with some velocity and this object has no velocity and they collide, one object has a new velocity, we can calculate what this velocity is. This is just momentum, linear momentum. And so I need some space. And so hopefully you all have that written down. You can go back and write it down. We're going to say M1 V1I plus M2 V2I equals M1 V1F. Okay, we've done this before. Let's call this the ball, and this will be the rod. And so this will also be the ball, and this will also be the rod, just so you can see where I'm going with all this. So before the collision, before the doink, the mass of the ball is m, its velocity is v naught. The rod has no translational velocity, so its initial linear momentum is 0. And so we'll say equals. Now after the collision, the ball has mass m, and velocity is negative v naught over 4 plus the mass of the rod is 6m, and its new velocity, well, we don't know what it is, but we're just going to call it v. And we're going to solve this equation for v. So I'm just going to make this look a little bit nicer. This is negative m v naught over 4. And just keep in mind that v naught is supposed to be a subscript. Kind of write it terribly on the iPad. And let's just solve this for v. V is not v naught, by the way, so we are not going to cross them out. We can cancel, though, an m. So we have v naught is negative v naught over 4 plus 6v. Let's add v naught over 4 to both sides. A v naught plus a 1/4 v naught is 5 v naught over 4 equals 6v. And then we'll just divide by 6. So this is 5 v naught over 24. So it's an interesting result. The velocity of this rod is 5/24ths of the initial velocity of the ball. Cool. And I think that's it.